Alright, so we've got problem 19.7. A simple pendulum consisting of a bob attached to a cord oscillates in a vertical plane with a period of 1.3 seconds. Assuming simple harmonic motion and knowing that the maximum velocity of the bob is 0.4 meters per second, determine the amplitude of the motion in degrees and the maximum tangential acceleration of the bob. Okay, so we start out with our harmonic motion equation. So we've got our equation for theta, which is equal to theta sub m times sine of omega n times t plus phi. And then we've got our equation for omega n, which we can plug in our known values and solve for that and get omega n equals 4.833 radians per second. And then we're going to move on to our theta dot equations and our v sub m equations. And we can obtain from those our theta sub m equation, which equals v sub m over L omega n. My bad. And then we've got our simple pendulum equation for our omega n, and that's the square root of g over L. And then we can manipulate that to find our equation for L and solve for that. And then plug that into our theta sub m equation from earlier and solve for theta sub m and get theta sub m equals 11.29 degrees. And then for part B, we start out with the equation for maximum tangential acceleration, which is a sub t equals L times theta double dot. And then move on from there and get our theta double dot equation and simplify that and solve for a sub t sub m, and then plug in our known values and get that a sub t sub m equals 1.933 meters per second squared. Alright, problem 19.23. Two springs of constants K2 and K1 and K2 are connected in series to a block A that vibrates in a simple harmonic motion with a period of 5 seconds. When the same two springs are connected in parallel to the same block, the block vibrates with a period of 2 seconds. Determine the ratio of K1 over K2 of the two spring constants. Alright, so we start out with our equivalent springs equations. So we've got our springs in series and parallel. So we've got those two equations. We've got our K sub s and our K sub p. And then we're going to take our tau sub s equals 2 pi over omega s and our tau sub p, which is the same thing, over omega p. And then we know the relationship between omega. So omega equals k sub s, k over m, so and it's both for s and p. And then we're going to take our equation for tau sub s over tau sub p, square that, and substitute in our values of k, and solve that for our k1 over k2, and substitute our 5 over 2 seconds there. And then just solve that down for k1 over k2, and that equals 4. Alright, problem 19.30. A 40 millimeter deflection of the second floor of a roof of a building is measured directly under a newly installed 3,500 kilogram piece of rotating machinery, which has slightly unbalanced rotor. Assuming the deflection of the floor is proportional to the load it supports, determine the equivalent spring constant of the floor system and the speed of RPM which the rotating machinery that should be avoided if it is not to coincide with the natural frequency of the floor machinery system. So we start out with our equivalent spring constant. We've got W, the equation for W, and K sub E. And then we can plug in our known values there and get K sub E equals 858 newtons per millimeter. And then for our part B, our natural frequency equation is F sub n equals the square root of K sub E over m all over 2 pi. And then okay, problem 19.39. A 6 kilogram uniform cylinder can roll without sliding on a horizontal surface that is attached by a pin at point C to the 4 kilogram horizontal bar AB. Bar is attached to two springs, each of a constant K equals 5 kilonewtons per meter, as shown. Knowing that the bar is moved 12 millimeters to the right at the equilibrium position and released, determine the point of vibration of the system and the magnitude of velocity of the bar AB. Okay, so for part A, we start out with our mx double dot equals 2kx minus p, and then our part B is mx double dot equals p minus f. And so we've got our equations there, and so we're gonna go through and solve. I went through and solved those for omega n, and you get omega n equals 27.73 radians per second, and then from there we use our tau sub n equation, which is 2 pi over omega n, and solve that, plug in our omega n, and we get tau sub n equals 0.227 seconds. And then for part B, our Vmax equals 12 millimeters times omega n, which equals 333 millimeters per second. Alright, so problem 19.64. Alright, a uniform disc of radius 120 millimeters is welded at its center to two elastic rods of equal length and fixed at the ends A and B. Knowing the disc rotates through an angle of 8 degrees when a 500 millinewton times m couple is applied to the disc, and that it oscillates with a period of 1.3 seconds when the couple is removed, determine the mass of the disc and the period of vibration if one of the rods is removed. So we start out with our spring constant equation, which we've got T over theta, and we can plug in our known values and solve there, and we get K equals 3.5 newtons times meters over radians. And then for our equation of motion, we have our sum of m naught, which corresponds to the equation negative k theta equals I theta double dot. And then we have our equations for natural frequency and period. So we've got our omega sub n squared, and our period equation, which we've been using, our tau sub n, and then our moment of inertia, so I. And I we can solve for, we can plug in our known values and solve for I, and then that makes it so that we can solve our equation for m. So we solve for I, and then we use our equation for m from the I equation, solve that for m, and get m equals 21.3 kilograms. And then solving for the second part of the problem, the one rod removed, we've got our K prime equation equals K over 2, which is equal to 1.791 newtons times meters over radians. And then just plug that into our tau equation from earlier and get tau equals 1.838 seconds. Alright, problem 19.79. Okay, so this is the problem. A 15-pound uniform cylinder can roll without sliding on an incline and is attached to a spring AB as shown. If the center of the cylinder is moved 0.4 inches down the incline and released, determine the period of vibration and the maximum velocity of the center of the cylinder. Okay, so we've got our the two positions. We've got position 1 where we've got T1 equals 0 and our equation for V1. And then we've got our T2 and V2 equations for position 2. And then we derive our through conservation of energy, we've got our T1 plus V1 equals T2 plus V2. We enter those two equations in there and simplify them down to get one final equation. And then we move on to... Alright, so next up we've got problem 19.91. The 20-pound rod AB is attached to two 8-pound discs as shown. Knowing that the disc roll without sliding, determine the frequency of small oscillations of the system. Alright, so we start out with our masses and moments of inertia. So we've got our MA equals MB equation, which we can solve. And then we've got our I bar and I bar A and I bar B. And that is equal to 1/2 m sub a r sub a squared. So we can plug that value in. And then we've also got our m sub ab, which we can find with the given information. And then our v bar and our v sub ab. So then we move on to our position 1, which at position 1 we know that T1 equals 0, and we've got our equation for V1 here. And then our position 2, we've got our equation for T2 there, which is pretty complicated, and we can plug in our known values for those and get that T2 equals 0.1018 times theta dot sub m squared. And then we've got our equation for V2 equals negative W sub AB times 4 out of 12. And now finally, with our conservation of energy, we've got T1 plus V1 equals T2 plus V2, as we know. And then we substitute our equations that we found earlier for those, and then we can solve that for theta sub m and get that theta sub m equals 5.7 times theta sub m. And then use our harmonic motion equation, theta dot sub m equals omega sub n times theta sub m, and solve that. We get omega n equals 5.7224 radians per second. And then for our frequency, we just plug that into our omega n over 2 pi, and we get our frequency equals 0.911 hertz. Alright, now for problem 19.95. A section of uniform pipe is suspended from 2 vertical cables attached at A and B. Determine the frequency of oscillation when the pipe is given a small rotation around the centroidal axis 0, 0, and released. Alright, so again we're going to work from position 1. We've got our T1 and our T1 is 0 and our V1 equals mgy sub c, which we can then substitute our y sub c for L times 1 minus cosine of alpha, and then use that equation and convert that into 1 minus cosine alpha equals 2 sine of alpha sub m over 2 using a trigonometric identity. And then we've got our V1 equals mgl times a squared over 8l squared times theta sub m squared. And then at position 2 we've got our equation for T2 and V2 equals 0. And then we're going to find our theta dot sub m equals omega sub n times theta sub m. And then again with our conservation of energy, we've got our T1 plus V1 equals T2 plus V2. Plug in those known equations there, and then just simplify them down, and we get f sub n equals 1 over 2 pi times the square root of 3g over L. Now for problem 19.95, a section of uniform pipe is suspended from 2 vertical cables attached to A and B. Determine the frequency of oscillation when the pipe is given small rotation around the centroidal axis and released.